Chemistry 3202 course overview, Unit 1, Section 1, Lesson 2, Potential Energy Diagrams. In this particular lesson, we're going to look at the energy diagrams for chemical reactions. And by taking a quick look at this image I have here on the screen, we can see that this bus would have different forms of energy, wouldn't it? The bus, it appears to be moving because of all the little jagged lines around it. So its moving energy would consider the fact that it would have kinetic energy. So the kinetic energy would be the energy of motion, okay, whether it be heat energy, light energy, sound energy, the movement energy where the bus is actually moving. That would be energy that's actually doing something. There's another form of energy here, of course, that's represented by the bus, and that would be potential energy or positional energy, in which case the bus would be having a certain amount of potential energy, gravitational potential energy, with respect to different points on the graph. All right, so if this bus was all of a sudden to give out and not run, the bus driver could simply put it in neutral and he could roll back down the hill to get home, or the bus driver should be able to roll the bus all the way to the school because it has potential energy. It's got stored energy from its position because the bus is higher than every other position on this diagram. All right, so potential energy, stored energy. The important thing is where the bus is located now and where it's going and its relative position between that. And the kinetic energy, of course, is its energy of motion. So we're going to focus more on the potential energy for the most part. Okay, here's a few outcomes that would be covered on this lesson. Okay, the very first thing we're going to look at is the idea of temperature and kinetic energy. And in this particular lesson, we're saying that kinetic energy is energy of motion. It's energy of movement. It's when things are happening. And kinetic energy, if something is moving, in order to get it moving, it's going to depend on two things. It's going to depend on how heavy the object is and how fast the object is moving. So for a physical point of view, I guess, the kinetic energy of an atom or molecule or some object that we're measuring, its kinetic energy would be based on the physics formula 1/2 mass times velocity square. Now a practical application here, we're not getting into any calculations with that, but a practical application here is saying, all right, we got a transport truck that's cruising down the highway at 80 kilometers an hour, and we got a little tiny smart car that's cruising down the highway at 80 kilometers an hour too. Which one has more energy? Which one has more kinetic? And the idea is, of course, that they're both traveling at the same velocity, but it's going to take a lot more fuel to get that transport truck moving to 80 kilometers an hour. It's going to burn more gas to keep going. So because the transport truck is more massive, it's going to be requiring more energy to keep it going at 80. Therefore, the kinetic energy of the transport truck has more energy because it's more massive, traveling at the same speed. Okay, we can take this and say, well, what's happening when we measure the temperature of, say, a cup of coffee, and we can see that at room temperature the thermometer was at 20. When we stuck the thermometer in the hot cup of coffee, the temperature started to rise to 70. So what's on the go there? Well, we can see that when the thermometer is placed in the coffee cup, the alcohol in the thermometer begins to expand. So how do we account for that expansion, that observation? Well, the idea being is the kinetic molecular theory is telling us that the alcohol that's inside the thermometer is in a situation now where molecules are colliding with the outside of the thermometer and transferring its energy to the alcohol. The alcohol molecules begin to gain this kinetic energy because of all the collisions, all that energy is being transferred. And as the alcohol gains energy, the alcohol molecules have to move further apart, and as a result of that, they get squeezed up the tube of the thermometer. So we can see that we can explain this observation of being able to measure kinetic energy with a thermometer as an explanation of the kinetic molecular theory. So when we measure temperature, therefore, temperature is an indirect measure of the kinetic energy or the motion of the particles inside the thing that we're measuring. All right, so temperature is an indirect measure of the speed of the molecules. And we can take a few more examples of this. Now when we take the temperature of something, we like to measure the average temperature. We have to keep in mind that what we're measuring is the average kinetic energy, it's not an absolute value. So here's an example that we can look at. Suppose you're sitting in your classroom there. There's 3 places where you can sit. You can sit next to this heater, in which case you're going to be very hot. Or you can sit next to this drafty window, in which case you're going to be very cold. Or you can prefer the coveted seat here right in the middle, where the cold air is beginning to mix with the warm air. And in the middle of this room, you're getting an average reading. And that's why the thermometer would be closer to the middle of the room. If you put it close to the heater, it's going to take an incorrect reading because it's going to assume the room is very hot, but it's not. It's only hot by the heater. Or if we put the heater, the thermostat close to the window, it's going to give us a false reading, assuming that the room is really cold. But by putting it near the middle, what we do is we get an average reading, assuming the energy is mixing within this room. All right. Now we can represent this graphically by saying, okay, if we look at the number of individual molecules, if we could count the number of individual molecules in this room, because most of them are in the center of the room, there's only very few next to the cold window, and there's only very few next to the hot heater. So what happens is, if we can draw a graph here, what we see is a nice bell curve where the largest portion of the molecules is going to be gathered around the average. All right, so this graph, the top of this graph here, the very highest point, is telling me what the average velocity or average kinetic energy of the molecules is, and that would be reflected as our T average. So if this was the water inside our hot coffee cup, we would be measuring 70 degrees Celsius because most of the molecules colliding with the thermometer would have an energy close to 70 kilometers. 70 degrees Celsius. Okay, there we go. Okay, so if we look at our thermometer case here, again, we're getting this average reading. So because we're saying the average reading is somewhere around 20, then the bell curve is going to represent a gathering around the 20-degree mark, and that would be our average kinetic energy. Okay, if we look at this in terms of again, percentage of molecules graph, we're looking at the low energy molecules here, and we're not talking about people in the room or anything. We're talking about molecules in a sample. We got some high energy molecules, some low energy molecules, and again, the average molecules in this sample are gathered around the average. All right, so this would be the average reading. Now, what does this mean for us? Well, remember we talked about the collision theory a minute ago in the last lesson there? The collision theory is telling us that we need sufficient energy. Molecules have to collide with sufficient intensity in order to cause a chemical reaction. Without that intensity, we won't get a successful reaction. So we can represent that successful energy point here on this graph and say, hey, we're going to call this the threshold energy, or this is the minimum energy required if the molecules are going to collide. So any molecules that are very, very high energy, if these molecules collide, then chances are they could be successful in causing a chemical reaction. All right, so these few molecules are the only ones that are going to have enough energy. Any molecules back here in this zone, none of them, if they collide, nothing happens because they don't have enough energy. So they have to have the minimum amount of energy, anything past the minimum, and now they're capable. No one says the reaction is going to happen, but now we're saying, yeah, if they have enough energy, that now it's more likely that a chemical reaction would occur if they did collide. So only these molecules have that energy. All right, now we want to reflect that in what's called a potential energy graph, because we want to be able to see how many molecules, what would be the potential for these molecules to start colliding. And the potential energy graph is showing us the energy of position. And here's a particular potential energy graph showing us the energy in the bonds between hydrogen and oxygen, and they want to chemically react to produce water, H2O. So what we're saying is that in order for hydrogen and oxygen to successfully collide, they need to meet that minimum threshold energy. So in order for this particular reaction to occur, the hydrogen and oxygen have to be in this excited state up here. They have to have that minimum amount of energy. If they don't have that minimum amount of energy right here, we can say, well, how much energy do they need? Can we give them a kick to get them over to that high energy state? And that's what we're looking at here. We're saying we know that we want to go from hydrogen and oxygen down to water, But before we can get there, we have to get these molecules excited. So we have to give these guys an energy kick. And that minimum amount of energy that's required is what's called an activation energy. So that highest point on the graph right there is that threshold energy. If we go back to our diagram over here, that is what we're talking about. Before we can chemically react, we have to kick those molecules over that threshold energy. We have to get to that side. So that's what we referred as the activation energy. Okay? And the activation energy is this value right there from the graph. So we would refer to it as an energy kick. It's the energy that's needed to get the reaction started. Once the reaction starts, well, it's all downhill from that then, right? All that energy gets released once the reaction starts. And this goes back to that gasoline example. If the gasoline is there mixed with oxygen, it may not chemically react because it hasn't been given the kick. So a lighter, static electricity, something to get it going, to get those molecules excited in order to get over that energy barrier. Okay? So we look at what's called an energy profile diagram or a potential energy diagram. Here's an example of a reaction that's going in both directions. So in the forward direction here, we're seeing that hydrogen and oxygen will give them a kick to get them to the top there. And then once they get to that top, it's all downhill after that. All right, excellent. So we give them a kick to get them over, and the forward reaction goes really, really, really quickly. So that's what they're referring to here as the forward activation energy. So this value right here is what's known as the forward activation energy. That's the energy kick that's needed to move forward. Now if we look at this particular reaction in the reverse direction, what we're seeing is that we can also go in the reverse. If I got water, I can start reversing this and saying, okay, but in order for me to reverse this chemical reaction, I have to get over a great big barrier. Just like going sliding. You slide down the hill, now you want to get back over. A lot of work to get back up to the top, isn't it? So in order for us to get back to the top, we have to put an enormous amount of energy in. We have to put in all this energy right here in order to get back to the top. Hence we call that the reverse activation energy, because now we want to go in the opposite direction. So this one here is the forward kick, small kick. The reverse kick is much bigger because now we have to go all the way back up over the hill to get back there. One thing that's common between both of them is the amount of energy that's stored. This heat of reaction is the stored energy. So if this is like our school bus and the school bus is going downhill, what we're seeing is that all this energy here is going to be released. The stored energy is being released. Okay, so all of that stored energy is going to be released as this chemical reaction goes forward. Let me just move this over here. Okay, now if we go in the opposite direction, we can't get something for nothing. If we gave away energy when we went forward, in order to go in the reverse direction, we now have to absorb the energy. Okay, so we have to give that energy back, and that's the difference here. Even though it's the same amount of energy, if I give you 50 kilojoules of energy when I release it, I have to put 50 back in. All right, so the amount of energy is the same, except that this guy is going to be a negative value because I'm releasing it. This guy is going to be a positive value. We're storing it. Okay, so a few words, a few terms that have to go along with this. An activated complex from this graph. This is the highest point on the graph. It's the point where we're not quite there. We're right at the very top. Let me just go back here. Activated complex. We're right at the very top here. We're right at the very top. If we slide back, then we go right back to hydrogen and oxygen. So we get energy, not enough, we slide back. Energy, not enough, we slide back. It's not until we reach the very top here, the activation energy, that we're at this activated complex. And if we go forward, then there's no going back. All right, so if we get enough energy to get over this little hump and start sliding here, once we start sliding on this side, we're going to go right to the other side. So this activation barrier, this very highest point, is what's called an activated complex. That's the point of no return. Once you get there and go to the other side, you're going all the way to the other side. Okay? So that's the activated complex. And we call it a transition point. It's not quite reactants, not quite products, depending on which way it slides. If it slides back, it goes back to the reactants, hydrogen and oxygen. If it slides forward, then it goes to produce water. So it's an activated complex. It's a single point. It's very unstable. And as soon as it slips one way or the other, of course, you either have water or you've got hydrogen and oxygen. Right? So there we go. The activation energy, we said, is the energy barrier to the reaction, the maximum amount of energy needed to start the reaction. And it's the difference between the energy of the reactants and the activated complex. I'll do a calculation now to show you. And the last thing here is the heat of reaction. That's how much energy is being stored by the bonds. It's the amount of energy is released from where hydrogen and oxygen go to water, or it's the amount of energy that's going to be stored if the water goes back the other way. All right, so that's the potential energy. Okay, so let's have a look at some of these calculations here. So the difference then, we have exothermic and endothermic. An exothermic graph is going to have a negative energy. It's going to be a loss. An endothermic is going to be positive. So what we mean by that is that as hydrogen and oxygen slide down to produce water, 283 kilojoules of energy is released. And it's the negative value because it's a loss of energy. We're now at a lower energy state than we started at, so we lost energy. So with exothermic, we're saying that energy is being released. And we can represent this in a chemical reaction because we can say that hydrogen reacted with oxygen to produce water, and it also produced energy. It produced 283 kilojoules of energy. So energy is a product. Okay? These guys tend to be very quick because they generally involve a much smaller activation energy, right? In order to go forward, I only have to go over this little energy barrier. In order for me to go backwards, I have to go all the way up here. So the forward reaction is going to be much quicker because it has a smaller barrier than the reverse reaction. If I compare that to the endothermic, so what I'm going to do is the exact same chemical reaction, but I'm going in reverse direction here. And what we're saying now is that, look, we got to go all the way back up over the top, but not only that, we have to go back up over that bump because the activated complex is going to be the same species in both of these graphs. It's going to be the exact same energy in both of these graphs because it's the same species. So for the endothermic reaction, we have to store all that energy. Energy has to go in, and for that reason, we're putting energy in. It's storing, so we're adding energy to the system. Okay, so in this case, the endothermic reaction is going to be energy being absorbed. And if I write the chemical reaction here for this, we can see that water plus this energy, water plus all this energy is going into making hydrogen and oxygen. So the energy is being absorbed, and energy is a reactant. So this would be endothermic. Okay. Here's a particular question that you might see on a public exam. It says the heat of reaction for the formation of water is minus 286. So we're saying, all right, that's going to be, if we're going to make water from hydrogen and oxygen, that energy released is going to be negative 286. So as we go from hydrogen to water, this difference here is going to be negative 286. It's energy released. So we're going to have to go over a little bump. Doesn't matter how big the bump is. Okay, and it says the activation energy for the formation of water is 112. So they just told us how big this bump is. This bump right here is 112 kilojoules. The question's saying we want to calculate the activation energy for the decomposition or the breakdown of water. And what they're really saying is, well, what's the activation energy for the reverse reaction? And if I want to go in the reverse direction, I have to get up over that hump right there. So my reverse activation energy is going to have to be, I got to go up to here, So that's going to be a plus 286 to get up there, and then plus the 112 to get up there. So the total energy that I have to add is going to be 398 kilojoules to get up to that activated complex, right? Because we have to get up and over that bump. And that's going to take 398 kilojoules. And there we go. Okay, here's a Jeopardy question. What's defined as being proportional to the average kinetic energy of the particles? And that would be temperature. That's too easy. Okay, here's another type of question you might see here. It says, which symbol represents the activation energy for the reverse reaction? Okay, so activation energy for the reverse reaction. Read the question very carefully. I'm going in reverse, so I'm going to start here, and I want to go all the way to the top. So what's that value going to be to get there? Well, that's energy value Y. W represents the heat of reaction. Okay, X is representing the forward activation energy. And Z is not representing anything. That's simply representing the energy of the activated complex, the absolute energy. It doesn't really represent anything because we don't start at 0. Okay, number 4, it says, what's the activation energy of the reverse reaction if the heat of reaction is minus 60 and the activation energy of the forward reaction is 40? So I'm just going to draw a quick little graph here. And I'm saying I'm going to go forward. The heat of reaction is minus 60, so I know that that's going to be released here. So it's going to be a graph that looks like this. And it says the activation energy forward is 40, so that's going to be a bump that goes up. And this bump going up here is going to be 40. And it's saying, what's the activation energy of the reverse reaction? So we just done one like that. I want to go in reverse, so I need to get up there. So it's going to be the 40 plus the 60 for a total of 100. And that graph, that pen is not a very nice color. Let's just change that to blue, and there we go. So the answer to that is going to be 100 kilojoules. And again, we know which way the graph is. It's endothermic or exothermic, so we can write the direction of that. Okay.